Good morning, everyone. Thanks very much, Professor Vishnu, for introducing me. And also thanks to Professor Kaushik for inviting me in this workshop. I have to say I really like Bangalore. This is my first time, but it feels like home because it's, very nice, a very green campus. It feels that I'm back to the university again because my university, when I did my bachelor in Dhaka, that had quite a similar campus and lots of buildings with complete maze and stuff where I was lost in the morning actually. I went to the computer engineering corridor and found this room, but then I had to come back again. Anyway, so today's presentation, I'll do some of my research, my group's research work on integrated power electronics for transportation electrification. Let's start. So I'm part of this Power Electronics Machine Center at the University of Nottingham. I'm not quite sure how many of you know this center, PMC Center. This is actually, we call it a PMC group, but it's a center in, let's say, American terms, because it's a group with, as you can see, with 21 academic staff, with almost 160 researchers, including 60 research fellows, which are postdocs, and 75 PhD students. We call ourselves one of the largest integrated power EMD group worldwide, and our main focus is on transportation electrification and energy conversion. So within the group, we have some academics looking at power electronics, some of them looking at machines, thermal management, module design. So there are different areas where different academics and researchers are working on. The group receives a lot of industrial grant, as you can see, 35 million active research grants, where 60% of the research is linked to the university. I'd like to say a little bit about our center. On here, you can see this is the building where we recently moved in. It's in the middle of 2021. This is a 35 million building project, so this is dedicated to this PMC only. And in here, we have state-of-the-art testing facilities up to 5 megawatt. So you can test 5 megawatt converters, drives, machines in this center. I think it's a very impressive facility. If you get a chance to visit UK, I'd highly recommend, please come to Nottingham and contact me. I'd love to give you a tour of this building. So today's presentation, as I said, I'll discuss, essentially my presentation will have two parts. One part is on power electronics integration. After finishing this part, I'll have a short Q&A session. And then I'll start my second part, which will be more about the power module integration and reliability analysis for power electronics converters and modules. So let's start with the first part. So what's the motivation for integrated power electronics? I think Professor Umanat set the scene this morning very, very well. He was mentioning a lot about the sustainability aspect of electric vehicle. So essentially, integrated power electronics is linked with the sustainable power electronics aspect. The concept is quite straightforward. Integrated power electronics enables high power density for power converters. High power density means you use less material when you design a converter. When you use less material, it translates into less emission. As you know, any material you use in a converter or a machine, it needs to be extracted in a mine, then it needs to be transported, then it needs to be manufactured. So if you can reduce the raw material, obviously you make the thing sustainable. So that's the motivation for doing research in integrated power electronics. Now, when you look at the low power electronics, for example, this kind of Traco power supply or Murata, will you raise your hand? How many of you have used these small DC-DC converters? I can see a couple of hands. But of course, if you designed any DC-DC converter or inverter in the gate drive circuit, if you buy it off the shelf or design it by yourself, it's highly likely you will use a small DC-DC converters like this. Now, these converters are actually designed in a more integrated way. If you look at the inside of this, you have some semiconductor devices, some wire bonds connecting the devices, passive components, all sort of encapsulated in the molded plastic, then you fill it with epoxy resin. So it's a compact design. Now, obviously, this kind of design you will not see in high power electronics. These converters are maybe maximum 10 watt. Okay? Why you cannot push power in this kind of arrangement? The main reason is the thermal. Okay? If you look at this design, it's very hard to get the heat out of the semiconductor devices in this kind of design. So if your power is 10 watt or 5 watt, the loss is too small, so it doesn't matter. But if you go higher power, kilowatt, tens of kilowatt, hundreds of kilowatt, this kind of arrangement is very challenging to get the heat out of this integrated packaging. Another thing is that they are not really low cost. So when I was designing inverters or DC-DC converters for electric vehicle, I saw that a majority portion of the bill of material was because of this. Because in an inverter, when you design the gate driver circuit, you may be using six of them, sometimes 12 of them. So that means the bill of material cost from these small DC-DC converters, they are actually increasing quite a lot. So they are not so low cost. Now, as I said, many medium or high power electronics, they are not even designed in this way. But integrated design is becoming necessary. It's because obviously you all know wide bandgap semiconductor devices such as silicon carbide and gallium nitride devices, they are entering the market. They are especially silicon carbide is replacing silicon in the automotive market quite rapidly. Now this obviously wide bandgap devices, their prime benefit is that they can switch really fast. Okay? So when you switch the MOSFET or any semiconductor device, MOSFET, IGBT, whatever, if you can switch them in really fast, that means your switching loss will be low, which means you can push the switching frequencies in these converters. And in some cases, DC-DC converters, these wide bandgap devices can reach up to megahertz. Now, when you go to that kind of switching frequency, now traditional design where you put the components on top of a PCB and have distance between gate driver and the power devices, they create obviously a lot of parasitic inductance, parasitic capacitance, so it's not really suitable for the traditional design. It's not really suitable for wide bandgap semiconductor devices. So that's why you need integrated design. Another thing is the optimal thermal management. So as you put everything more and more compact, it would be obviously challenging to get the heat out of the devices, whether it's the semiconductor devices or passive components. So optimal thermal management is another important design challenge for integrated power electronics. As I mentioned, in my group, two types of integration is being investigated. First one is the topological integration, which is where we are looking at multi-port converters, resonant converters, integration between machine and power electronics. And second is the power module level integration. When I say power module, I mean a number of semiconductor devices connected in parallel or series inside of a package. So that kind of integration, and also assessing the reliability of integrated power electronics. So first part, I'll go with the topological integration. So this is the first project I would like to highlight. This is called integrated OBC and DC-DC converter. So as you know, in any electric vehicle, you have an onboard charger. So this is that onboard charger, which usually part of the vehicle. It charges the high voltage battery, which could be 400 volt. In future, it could be 800 volt. And that onboard charger charges this high voltage battery. And also there is another small DC-DC converter, which is small, obviously in terms of power, slightly smaller than OBC, which is called 12 volt DC-DC converter. Because in like traditional IC engine vehicle, you still have a 12 volt battery, which needs to be charged. And that DC-DC converter charges the low voltage battery from the high voltage battery. The similarities between these two converters is that they are both isolated. So you need galvanic isolation in both onboard charger and APM. So what we proposed, instead of having two separate converter boxes in the vehicle, we proposed an integrated onboard charger. So essentially, it's a multi-port converter topology, where the input is your grid voltage, but the output is both 400 volt and 12 volt. So essentially, with this kind, you don't have to have two separate products. With one product, you can couple the grid to both high voltage battery and low voltage battery. So what's the advantages? Obviously, instead of two transformers, now we have one transformer. So it's a single isolation stage. So magnetic components volume we can reduce, as you will see in the next slide. And because of this kind of integration, we are sharing semiconductor devices. So we reduce the bill of material cost. And finally, another important benefit of this kind of topology is that from the grid, now you can charge both high voltage and low voltage battery. You can not only charge the low voltage battery from high voltage battery, but also you can charge it from the grid. So that's another benefit. And this is a benchtop proof of concept, 3.5 kilowatt, which is based on silicon carbide MOSFET. Now this is the circuit topology. As you look at the circuit topology, it almost looks like a hybrid between dual active bridge and phase shifted full bridge. So if you look at the power flow from this DC link to high voltage batteries, almost looks like a dual active bridge. If you look at the power flow from this port 1 to port 3, which is the low voltage battery, it looks like a phase shifted full bridge. But obviously, this kind of topology is easy to propose, but what are the challenges? First challenge is to design this integrated transformer. Okay, so obviously in this kind of topology, you need leakage inductances L1, L2, L3 to ensure zero voltage switching, and getting obviously precise leakage inductances from any transformer is challenging, as you all know. It is even more challenging in this kind of multi-port or three-winding transformer because modeling itself becomes quite challenging for this kind of transformer. Okay, second challenge, power decoupling. So when you transfer power to the high voltage battery, ideally you don't want anything happening to the low voltage battery. So you essentially you want to decouple the power flow from grid to high voltage battery and grid to low voltage battery. So that's another challenge because there is a transformer. So there is inherently there is a coupling here. And also you want to it's more linked, you want to independently control the charging of high voltage and low voltage battery. So what we proposed, not only this new topology, but also new modulation strategy. The purpose of this new modulation strategy is to have this power decoupling. So if you look at, I'm just briefly showing what's the modulation strategy here. Tau 1, tau 2, they are the duty ratios in port 1 and port 2. And phi is the phase shift between these between the primary and secondary voltages. Essentially, if you can play with these 3 degrees of freedom, and with certain combinations of these degrees of freedom, you can get power decoupling between the high voltage and low voltage battery. And also, because essentially how we control it, you use a lookup table, and I didn't show that in this slide. We put the input power, output power requirements, high voltage battery voltage requirements, low voltage battery requirements, and we created an optimization toolbox which generates the optimum tau 1, tau 2, and phi, which we put at the gate of these semiconductor devices to control the power flow in the high voltage and low voltage battery. And also, because we have this optimization tool, we can play with minimizing conduction loss. Certain combination of tau 1, tau 2, and phi will give you minimum conduction loss in this circuit. Obviously, you know, in this kind of converter, you have circulating current, which generates additional loss. And another important benefit of this kind of topology is there is no need for mechanical switches for power decoupling, so it can increase reliability as well. So what is the outcome? 17% volume reduction is achieved with the transformer integration. And we saw that with our modulation scheme, we can achieve zero voltage switching for almost all the loading operation and different, because these voltages, the high voltage battery and low voltage battery, they vary a wide range. And it's important to achieve zero voltage switching for all the different voltages of your high voltage and low voltage battery. So some experimental results, well, I think one of them is shown in here. As you can see, the green line, you can see it's the low voltage battery voltage, which is 14.5 volt. The purple color, that's showing the high voltage battery, as you can see it going from 350 plus to 350 minus. Then you have the primary side voltage as well and the current. Zero voltage switching, you can see in here, this is sort of a half power. So high voltage battery power was 1.6 kilowatt, low voltage battery power 450 watt. And if you look at the gate source voltage, if you look at here, obviously in all the turn on instant, the drain source voltage comes down to zero, then you have the gate source voltage. And we also look at the current as well. By looking at the current, we can also validate that we are achieving zero voltage switching. This is for S1, which will be similar for S2. This is for S4. Again, it will be similar for S3. So all the 4 switches in port 1. And again, similar things you can see for Q1, Q2, Q3, Q4, which is the 4 MOSFETs in port 2. Similar results at rated power, 3 kilowatt, 450 watts. So the total power of the converter is 3.5 kilowatt. You can see the 0 voltage switching transition for all the MOSFETs in the converter. Now, we are trying to build, we see that this is a topology may be really useful for the Indian market, because in India you have 48 volt batteries in 2-wheelers and 3-wheelers. So, and also in future, the electric vehicles will obviously have 400 volt battery, which is the traditional voltages. But even it is, if the voltage rises to 800 volt, with this kind of topology, you don't need 2 separate charging stations. Essentially, on the street nowadays, you can see the charging station. I think Ether and some other companies are putting the charging station, but that's only giving you a 48 volt output. With this kind of charger, you can charge essentially both of your electric car, which is 400 volt battery, and your electric scooter. So we are making another prototype, which is around 10 kilowatt, which I was hoping to bring it with me, but it's not finished. But I hope that we should be able to finish it and send it here for some testing, and which already we built already the DC-DC side of the converter, and which is shown in here, and just need to incorporate the AC-DC rectifier stage so that it's a complete prototype which can be used to charge 400 volt and 48 volt batteries in any application pretty much. It's both constant voltage and constant current charging mode. Yeah. Yeah. So you said that if you are doing in constant current, then obviously you try to fix the current in here, and power will gradually increase as the voltage increases at the battery. And you use that dynamic power change in your lookup table to generate the 3 degrees of freedom to control the MOSFETs. At the end of the day, I think we will still do constant current and constant voltage charging. So it's just an outer control loop, as I just mentioned, and which will create the references, the power references and the voltage references for our controller, the control algorithm, and which will spit out the different. So it doesn't matter in the outer loop what's your loop, let's say the controls strategy. Inside of the converter or inside loop, the strategy would be still the same. Okay. Now, if you are charging this battery, it can go from 8 volt to 14.5 volt. So if you think of a charging scenario, the voltage across this battery could be between 8 and 14 volt. So it's not fixed. Yes, once it's charged completely, it stays to a fixed voltage.
The high voltage system, you have some stepped kind of waveform, right? For the high voltage battery, you have.
Oh, right. So you mean in terms of here, the current waveform? No, so there would be a filtering capacitor here. Yeah. So which will filter the ripple, and it will be a DC current, obviously.
Okay. Thank you.
Yeah. Right, okay, so next project I'll like to talk about is this, what is called dual interleave boost converter. So interleaving technique is again another integration technique which is really popular over the years. And this is something we did to look at the fuel cell electric vehicle. So you know, fuel cell electric vehicles, their fuel cell voltage is slightly lower compared to the drivetrain voltage. So you essentially need a boost converter, okay? So in Toyota Mirai, they used a 4-leg interleaved boost converter. So here we are doing with a 2-phase interleaved boost converter. As you can see, Q1, D1, and one of the inductor will create one boost leg. Q2, D2, and one of the inductor will create another boost leg. So essentially 2 boost legs connected in parallel. So the clever thing is that this magnetic components, what we call IPT, interface transformer, okay? So this is a cross-coupled magnetic components. So essentially what we have seen that you can do it in two ways. One way is to have separate inductors in each boost cell, and another way is to have this coupled inductance and another small filter inductor, okay? And what we have seen that this combination can reduce the volume of the magnetic significantly. Why? If you look at the coupled inductor, the current, obviously the current IL1 will be distributed in the two windings because it's coupled, so which means the DC flux will be cancelled out. The only flux these magnetic components will see is the AC flux, which will depend on the voltage across these two terminals, and which means that this magnetics can be a little bit smaller. And obviously what you can do, you can have a high leakage inductance for this IPT, then you will not even need this inductor. But if essentially getting a high leakage inductance means you have to increase the size of the IPT anyway. So what we have seen that having a low leakage inductance plus adding an extra additional filter inductor can reduce the size of the total magnetics. So this is called, but this is a hard switching converter. So still you have switching losses in here. So what we have seen in multi-kilowatt converter, when you push the silicon carbide based MOSFETs to 75 kilohertz or 80 kilohertz, you no longer have benefit, or essentially the losses in the devices are so high that you cannot use them. So what we wanted to do is to use soft switching or resonant technique. And this is a, well, widely discussed soft switching technique called snubber assisted zero voltage, zero current switching. Again, if I want to explain it very briefly, Q1, D1 and L1, this is the boost cell, okay? This is a single phase simple boost converter. All the red bits are additional components. And this is a resonant network. Essentially, if you look at the snubber capacitor, CS is actually connected between drain and source of the MOSFET. So what you do, you just turn on the auxiliary switch slightly before you turn on the MOSFET Q1. And because of this, it's like maybe 100 nanoseconds or 200 nanoseconds. And during that period, snubber capacitor resonates with the auxiliary inductor. And when during this resonance, the voltage across the snubber capacitor gradually decreases to 0. So which means the voltage across the device gradually decreases to 0. Then the current in the device starts to flow. And this way, we can achieve zero voltage, zero current switching. So essentially, we remove the switching loss from the turn on instant of this MOSFET. Now, we implemented it in dual interleaved converter. So what's the benefit of this topology in dual interleaved? Again, if you look at here, each boost cell normally needs one auxiliary inductor. Because we are interleaving, we do not have to have two auxiliary inductors. We can just use one auxiliary inductor, and that auxiliary inductor is shared between the two resonant network. Okay? And same approach, before turning on Q1, you turn on the auxiliary switch, and CS1 resonates with L auxiliary, which gives zero voltage switching for Q1. Before turning on Q2, you turn on Q auxiliary 2, which means CS2 resonates with L auxiliary, and give you zero voltage switching condition for Q2. So some more details, I will not go through those details. There are journal papers on this, so you can have a look. But I just want to explain how the resonance works. If you look at here, this is the pulse for Q2, the main switch. This is the gate pulse for auxiliary switch. As I said, the auxiliary pulse starts a bit early compared to the main switch pulse. And when you give the pulse to the auxiliary switch, the first subperiod, current actually commutates from the diode to the resonant branch. So before you give the pulse to auxiliary, the current was flowing through the diode. And once you give a pulse to the gate pulse to the auxiliary switch, the current commutates from the diode to the auxiliary branch. So which means it's not moving. Hang on here. Okay, yeah. So first subperiod, this is the commutation period. As you can see, because there is an inductor in the resonant network, this current doesn't rise abruptly. So you have a gradual current rise. So yes, you can essentially achieve zero current switching for the auxiliary switch as well. Second two subperiods, you have that resonance that I described. the snubber capacitor resonance, you have this resonant current. And in the final sub period, the current again goes back from the auxiliary loop to the main loop. Okay? And if you see this during this resonance period, the voltage gradually comes down to 0. And once the voltage across the MOSFET, which is Q2, comes down to 0, then the current starts to flow initially through the body diode, then goes to the channel of the MOSFET. Okay? So two benefits from here. You can achieve 0 voltage, 0 current switching. You remove the switching loss. And also you can control the DVDT, which is very important in a lot of silicon carbide or gallium nitride based wide bandgap semiconductor device based power converters. So some experimental results from this 20 kilowatt prototype, again with silicon carbide. If you look at the gate pulse, the red one is the auxiliary, blue one is the main switch, and this is the advanced time. As you can see, during this advanced time, we have this resonating current flowing through the auxiliary loop, and the voltage comes down to 0. That's the drain source voltage, green line comes down to 0. Then we give the gate pulse to the main switch. Similarly, for Q1 and Q2, we can see the 0 voltage, 0 current switching transient. Okay, so like any other resonant topologies, this topology has a problem. Okay? This loses soft switching when the duty ratio of the DC-DC converter is below 50%. Okay? Why? You need a certain amount of voltage difference between the snubber capacitor and the input voltage to make sure the snubber capacitor discharges to 0 during that resonance period. If the voltage difference is not enough, the snubber capacitor voltage cannot come down to 0. And if you have some voltage across the snubber capacitor and suddenly turn on the MOSFET, what will happen? The snubber will discharge through the channel, which will create loss. Now, in a boost converter, obviously when the duty is less than 50%, you don't have enough output voltage, which means you don't have enough voltage across the snubber capacitor, which means you lose soft switching in this topology. So that's why we proposed another topology where we replaced, you remember there was an inductor in here, we replaced it with a pulse transformer with a 1:2 turns ratio. What the pulse transformer is now doing, instead of seeing the resonant network seeing the whole input voltage, it's now only seeing the half of the input voltage. So essentially, the input of the resonant network, you have reduced it. You've reduced it to half, which means now you can achieve 0 voltage switching no matter what's the duty ratio. Okay? Another thing we need to add here is this diode, because you don't want the current to flow in this resonant network in normal operating condition, because we want only this network to work during the turn on instant or turn off instant. So that's why you need to add this diode, and this diode, when it turns off, it creates a resonance with the magnetizing inductance. To suppress that, we need an RC snubber circuit. So again, if you look at from the same converter, we replace the pulse resonant inductor with a pulse transformer. They are pretty much the same size. And if you look at here, again, you can see the 0 voltage, 0 current switching. The drain source voltage comes down to 0. At that time, the device current is negative, which means the body diode is conducting, which means you achieve 0 voltage, 0 current switching. You can see it for both Q1 and Q2. And this is at duty 0.45. So you can see that even duty less than 50%, we can achieve 0 voltage switching with this new topology. One of my students is trying to extend it even further, because all these topologies, because as I said, we are looking at fuel cell vehicle, they don't have to be bidirectional. So these topologies are unidirectional. So he's looking at try to make something that's bidirectional, which he came up with this new topology again, which we call it unbalanced capacitor voltage DC-DC converter. So this is bidirectional. What does it mean? When the power flows from V1 to V2, it's buck. When the power flows from V2 to V1, it's boost. So any sort of DC link connection where you need bidirectional power flow, you can use this topology. So what's the clever thing in here? So normally, when you have a DC link capacitor series connected, you want the voltages to be balanced between the two capacitors. However, in this topology, we want the voltages to be unbalanced deliberately by controlling these auxiliary switches, because if we can reduce the capacitor voltage significantly lower than the input voltage, we can achieve 0 voltage switching for the wide range of operating condition. For a wide range of load condition, for a wide range of duty ratio, we can achieve 0 voltage switching. So that's why we call it unbalanced capacitor voltage DC-DC converter. What's the benefit? Simple structure and control system, no need for capacitor voltage balancing. We can achieve again 0 voltage switching for all the switches, 0 voltage switching for full duty ratio and load range. In some cases, you might ask, why adding these extra bits, not this topology, even to other topologies? I just want to mention this circuit is very small compared to the whole circuit. Okay? For example, in this topology, the auxiliary inductor is actually 80% smaller than the main inductor. Okay? So, and also, even if you consider there will be additional losses in the auxiliary circuit, still you get benefit, because these converters, we are switching at very high frequency. In this topology, this prototype, we switched at 100 kilohertz to 200 kilohertz. And as you can see, there is a clear 2 to 3% efficiency, or in some cases, 4% efficiency benefit between the hard switching and the proposed soft switching topology. So this is the boost version. So this is the buck version. Again, from the waveform, you can see the drain to source voltage comes down, and you have a negative current in the switch. So that means the body diode is conducting, which means you are achieving zero voltage switching. And this is the buck mode operation. So when the boost mode operation, when the power flows from right to left. And again, same circuit. Here I am showing you the ideal waveforms. Similar type of approach in terms of control. Before you turn on the main switch, you just a little bit early, you turn on the auxiliary switch. The one difference with other topologies here is that the current here becomes negative. In the auxiliary branch, the current becomes negative because it just has the body diode. Okay? So it cannot block the negative current, and essentially we need this negative current to maintain the unbalanced capacitor voltage, in this case at the output of the converter. So, and also we are showing that yes, you can achieve this unbalanced capacitor voltage no matter what's the duty ratio. So in this converter, whether the duty ratio is 0.1 or 0.9, in worst case, as you can see, the voltage across the C2 is only 18% of the output voltage. And to achieve soft switching, we need to make sure VC2 must be smaller than half of the output voltage. So essentially, no matter what's the duty ratio, we are achieving unbalanced capacitor voltage, which means we can achieve zero voltage switching for the whole duty range. Here are some experimental results. Again, these are for boost mode, 200 kilohertz, when the duty is 0.4 and duty is 0.52. So in both less than 50% and more than 50% duty. If you look at the waveforms, when the drain source voltage comes down to zero, you have the negative current, achieving zero voltage switching. Again, in other condition, you are achieving zero voltage switching. You can see the blue line is the auxiliary current. As you can see, the negative current in the auxiliary circuit, same in here. And on the right hand side, you can see the unbalanced capacitor voltages. And you can see this voltage is quite stable. So the VC2, so when the output voltage is 400, the voltage is divided into 343 and 53 volt. When the output voltage is 500, the voltage is divided between 436 and 53.4 volt. So you can still achieve stable, unbalanced capacitor voltage. Next project we are looking at is this integrated onboard charger and drive. This is a more, I think in the EV industry, it's more common because Renault Zoe already showed this technique of integrating the charger with the drive to, and sort of one of their, this is from one of their patents, where essentially they're using the winding inductances for filtering purpose, so reducing the size of the converter significantly. Unfortunately, Renault actually stopped this technique for their newer version. The reason is this converter that they built is a 43 kilowatt charger. And nobody in Europe charges, uses a 43 kilowatt or have a 43 kilowatt outlet at home. At home, you can only charge it at 3.3 kilowatt or 6.6 kilowatt maximum. So essentially, all the people who bought this Renault, they were charging their vehicle at a very low power compared to their onboard charger, which means the efficiency was scrapped, and they are eventually scrapping it for their future products. Another problem, as you can see, this charger doesn't have any galvanic isolation. So as Professor Umanad said, vehicle to grid will be the next big thing if we can sort out the battery lifetime and battery degradation issues. So essentially for vehicle to grid operation, this is not possible. So in our case, what we are trying to do, we are trying to use, first of all, well, there are also other challenges. One is the torque production during charging. So when you charge a vehicle, usually the vehicle is stationary, okay? But the current is flowing through the winding. So that means there will be some ripple torque. And you need to use the brake, so which means it's dissipating energy. So the system is lossy. So you need a mechanical lock system. And also sometimes this kind of charger, they have pulsating power, which can reduce battery lifetime. And also now the power modules, so you are using the power modules of the inverter twice now. You are using it to drive the vehicle and also to charge the vehicle. So as you'll see from my slides in the second part, this also impacts the reliability issues of the semiconductor devices. So what we are trying to do, this is an early stage of the project. What we are proposing is to, instead of a 3-phase machine, maybe use a 6-phase machine. And this additional interface, so we are planning to use like topology like 3-phase DAB, where you will have a transformer, but that's a high frequency transformer, so it will be significantly smaller. And you can still use the winding inductances for the filtering of the input so that your input is smoother. So you don't have to have a large LC filtering circuit in your converter. And from the simulation, we can see you can still achieve benefit in terms of improving the power density of onboard charger, even when you design a charger at the rate of 22 kilowatt, which is common. In 3-phase, you can go up to 22 kilowatt, even at households. And in single phase, you can go up to 6.6 kilowatt. So I'll stop here. I know I've shown you a lot of different circuits. So if you have any questions on this part of the presentation, please ask, and then I'll probably start the second part.
Is that the reason?
Oh, which one? This?
The advantage that you just showed here, high power charging.
Yeah, that's high power is not fast charging. This is still the prototype. For example, the prototype we built for, as I said, with code.
Trying to understand.
That's still a 6.6 kilowatt. So it's not a fast charger.
Okay.
It's faster than your,
the
normal charger, but still it's not a 50 kilowatt or 100 kilowatt or 200 kilowatt fast charger. And because you cannot, these chargers are onboard chargers, okay? And so you cannot put them, you cannot put a 100 kilowatt onboard charger in the vehicle because it will take up a huge space in the powertrain.
Okay, so it's still the normal charging,
but slightly higher power.
Slightly because of the power, high power there.
Yeah.
Thank you.
Sir, I want to know that the bidirection mode you were showing in that converter. So in that, it is working both at a time, boost and buck, or only at a time?
One at a time.
One at a time.
Yeah. So essentially, if you think about an EV application, for example, this could be your battery, and this could be your drivetrain. So this is when the power flows from the battery to the drivetrain, and when the reverse condition, when the power flows from braking. For example, when you're braking it, power flows from the drivetrain to the battery. So it is not happening at the same time. It's not a buck boost converter. It's forward buck, reverse boost converter. Yes, yeah. So minimum, as I said here, 50% unbalance required. VC2 must be smaller than half of the output voltage. So as long as we can make sure VC2 is less than V out divided by 2, we can achieve soft switching for the wide range of operating conditions.
How to maintain that unbalance?
So what happens during the startup phase of the converter, we switch the auxiliary network in a way to create an unbalanced voltage between the two capacitors. And when the resonant network works, the way the converter works, that unbalanced voltage is maintained even after the startup position. But at the startup, we do some modulation to make sure we create an unbalanced voltage between the C1 and C2. We have got a IEEE transaction paper. If you want, you can have a look at it.
With respect to your previous circuit, the boost with the inductor, though the inductor size is reduced, there are some auxiliary inductors added, right?
Yeah, this is the auxiliary inductor, yeah.
Not this one, sir. I think probably the next slide. The final, yes, exactly. Sir, due to addition of all these, does it have any impact on the EMI profile of the system?
Well, there will be more resonance in the, because of the, that's why we put this RC snubber circuit. So if you don't put this RC snubber circuit, what will happen when the diode current goes down to 0?
Yes.
There is a diode capacitance, right? That diode capacitance starts to resonate with the magnetizing inductance of this. To suppress that high frequency oscillation, we connected this RC snubber circuit. So you're right, there is an EMI issue, but we sorted that out with this RC number. And even if there is any additional EMI issue, you can connect, chokes in here to suppress that as well.
So you started with, to mitigate the hard switching in the boost converter, you started with this topology. So my doubt is still this is a type of conventional AC to DC, then DC to boost. So compared with the totem pole newer version, which the efficiency point of view, adding more and this auxiliary circuit and getting a soft switching compared to that with a totem pole, which will be much.
Sorry, we haven't done that analysis or comparison with the totem pole, but this type of auxiliary network is common even for AC-DC or DC-AC application. Look at the papers of ARCP converter, auxiliary resonant commutation pole converters. Okay, if you look at papers searching ARCP, you will find DC to AC converters using this kind of resonant network. And probably one of those papers might have compared with totem pole, but we haven't done that.
I think we should move.
Okay, yeah.
Yeah. So you can catch hold of Professor Rishad during lunch break if you have more questions on this. We'll move on to the next part of the talk.
Right, okay, so as I said, in the second part, I'll discuss more about integration of power modules. So it's a packaging integration, and I'll also discuss some of the reliability work that we are doing. So the first project I would like to talk about is this 3D integrated GaN power module, okay? So essentially this is a project funded by Automotive Tier 1. As you know, in future automotive, there is a tendency to put power electronics close to the machine. So they are, again, it's link up with the wide bandgap semiconductor devices. You want to reduce the parasitic inductance. Also, you don't really want a high distance between your inverter and the machine. So that's why more and more automotive tier 1s are coming to us to make sure creating packages which can be connected very close to the machine itself. So one approach is to integrate the GaN modules vertically within the PCB. So what's the 3D integration? So in traditional circuit design, we put components in X and Y direction, right? In 3D integration, you not only put components in X and Y, you can put components in Z direction. So you stack up the components. So one benefit is that you are not losing the FR4 area, so you can put the devices right inside of the FR4. So as you can see in here, so this is the GaN device, and essentially this is sort of centered on top of a DBC, and then underneath you have some cooling plate, and on the top side you have the FR4 materials which can be drilled via laser, then electroplated to create connections with other components. So essentially you can bury the GaN devices within the FR4. Now, obviously, one benefit is that you reduce the size of the module, and also you reduce the size of the parasitic inductance, because now the gate driver is very close to your HEMT in this case, which is obviously gallium nitride high electron mobility transistor. Another issue with the GaN devices is that they are several times smaller than silicon, so they are tiny. If you look at the GaN devices, they are tiny. So it's always challenging to get the heat out of those devices. So with this kind of embedded technology, you have the heat pad, or the thermal pad has a direct connection with the cooling plate. So which means again you get some thermal benefit. So we've done some very simple embedding simulation, and in the lab we have some processes, because in terms of process it's quite similar to a PCB manufacturing process. You still need to put FR4, then you need to sort of cure the FR4, then drill the holes that you drill for vias, then electroplate it. The only challenge here is that obviously GaN devices, as I said, the devices are small. The pads are even smaller. So having a high accuracy laser which can detect those pads once you bury them inside of the FR4, that's one of the challenges. But some of the simulations that we do, we can see that one benefit, you can suppress the false turn on and reduce EMI, because in GaN switching devices, the gate loop inductance or common source inductance, they are killer inductances. They can cause shoot through or false turn on, which can increase the losses. So we saw that with this kind of integration, you can suppress that. High power density, so if you look at this is a GAN systems like a prototype module, which is a half bridge. And if we build a similar module with 2 devices in parallel, and this is the bottom device, also with the top device, with the gate driver integrated, our modules will be 2.5 times smaller than the GAN system 650 volt, 150 amp power module. And also it can enhance the packaging reliability because we don't have solder joints anymore. It's either sintered joints or direct copper joints. And it can be used in challenging environment, as I said, automotive or even other environment like mining, where you have high temperature, reduced space, and low weight requirements. So again, now this slide, I'll delve more into the reliability issues, first with the power module. So one of the problem with automotive application of these power modules is that you have reliability issues. The modules start to fail. So first I will explain why that happens. So if you look inside, if you do a cross section of a conventional IGBT module, you will see these layers. So you'll have maybe the IGBT with the diode, and you have some wire bond. Then they are sintered or soldered on top of a DBC substrate. That DBC is then soldered on top of a base plate. Then the base plate is placed on top of a thermal grease, which is placed on top of a heat sink. That heat sink can be liquid cooled or air cooled. Now, if we look at the thermal properties of these different layers, as you can see, they have different resistivity. So thermal grease has the highest, and then obviously silicon die or copper, they have the lowest thermal resistivity. So getting the heat out from the die to the heat sink to the cooling material, which can be a liquid coolant, obviously it's challenging. Another issue, all these different materials, they have different CTE, so coefficient of thermal expansion. Now, these modules are constantly seeing large delta T. So when you start accelerating, you put more power into these modules. So essentially, you heat up these dies. Then once you start cruising on the highway, you take the foot off the accelerator, then the power level of the inverter comes down, which means you are cooling down these devices. So always you have high delta T variation at the junction of these MOSFETs. So what will happen if you have a high delta T? Obviously all these materials will expand and contract, expand and contract. And if they don't expand and contract at the same rate, you will start seeing crack in weak points. In these modules, the weak points is the hill of the wire bond. And we have run accelerated life test, we've x-rayed this module, and we can see the hill crack here. And we have seen also, when I was working in Dynex, we built double-sided cooled module. So we replaced the wire bonds with a copper moly, so it's just small little bumps of copper moly, and put 2 DBC, so sandwich the devices between the 2 DBC. Even after doing that, when we run the power cycling test, so when we heat up the devices and cool down, heat up, cool down, we'll see that the device starts to fail, and starts to fail where for example, the copper moly is connected with the device. So it's an inherent problem. You cannot, there is no silver bullet to solve it, because how the module constructs, you will always have different materials which will have different CTE, and which will create these reliability issues. Now, the thing I'm trying to do in my research is not to solve this, not to obviously invent new material, but how we can model these reliability issues and monitor the health of the modules. So this is an example. So this is a simple inverter which we are using Hitachi modules. This is a road pack module, so state of the art with copper wire bonding, sintering, etc., etc. And then it's connected with the machine, let's say. So this is based on Plex simulation. So that we have a thermal model for the module, and we have a load profile which was provided by our, let's say, the collaborator, one of the TR1. So we put this load profile into the simulation, and based on this load profile, we can generate a junction temperature profile, okay? And that junction temperature profile, from that we can put a algorithm called rain flow algorithm, which will convert this junction temperature profile into a set of delta T's. And we can also get this lifetime models. So usually lifetime models we can create those models as well. Essentially, you run these modules at different delta t's and find out how many cycles it takes to fail these modules. Then you fit a line for delta t versus n, which will give you a lifetime model. So what we are using, well, in our let's say software, the Tj variation is converted into a lifetime number or life consumption number. So essentially, each time we have a driving cycle, analytically, we can estimate what's the percentage of life consumed for these modules. So that's what we call a MATLAB-based offline lifetime estimation model. We're also investigating into online lifetime estimation model. So online models, we need to measure the device RDS on or threshold voltage, because what we have seen as we age these modules throughout the time, we can see changes in the RDS on, we can see changes in the threshold voltage, because as you, obviously silicon carbide MOSFET, they still have some gate oxide reliability, which as the device aged, you can see some impact on the threshold voltage. And when you have this kind of hill crack, this will have an impact on the RDS on. So second part of this project is to look at this online measurement of electrical parameters to detect the health of the module. The objective here is to make sure you can create a limp home mode, okay? So when you drive the electric vehicle, you don't really want to be stuck on the highway when suddenly something fails. So essentially, by doing this kind of detection, the computer in your car can tell you that, you know, there is an imminent failure in maybe 1 hour or 2 hours. Please slow it down, reduce the power, and go to a garage, so you are not stuck on the highway. Similar type of thing we are doing with, these are with silicon carbide, this is with GaN, and this in here, we are more looking at the traditional circuit-based design, so where you have the GaN devices connected on a PCB and you have the gate driver circuit and everything. We are trying to find out with the GaN devices, with this circuit-based converter, when you heat up and cool down, what is the weak point? Because majority of the GaN devices doesn't have wire bond. Inside of these packages, you have copper pillars, so direct copper connections between the die and the pads of the devices. So we are trying to find out, in this case, we run temperature cycling. So we don't heat up just the device, we heat up the whole circuit. And then we can X-ray, after maybe thousands of cycles, we do 3D X-ray, and then try to find out if there is any crack in the solder, if there is any crack in the device, or if there is any crack in the copper pillars inside of the package. Again, essentially the outcome will be predictive maintenance or estimation of maintenance and repair costs. Finally, another reliability project. This is where we are looking at the DC link capacitors. So this is, it can be applicable to both automotive and industry, but this project is more industrial focused, where our industrial partner has usually they sell drives in hundreds or thousands in a plant, and they want to monitor the group of drive system. And in those kind of drives, usually it's the DC link capacitor that fails. So we created this, again, an accelerated life setup for the DC link capacitors. We put the capacitor inside of the oven, and then with a circuit which can be controlled by an IDAC, which is from LabVIEW, we charge and discharge it for thousands of cycles. And after maybe 1,000 or 500 cycles, we stop the test. We do a measurement of the LCR with an LCR meter for the capacitor. Again, try to find out what's the parameters are changing. As you can see, the capacity after 25,000 cycles, you can clearly see. So the blue line is the capacitance at 0 cycle, but as the capacitance age, the capacitance starts to drop. Okay, and with the challenge with the capacitance is that the modules, we can age the modules in a week or 2 weeks, and it will fail. But the capacitor will take months, maybe 3 months, 6 months to fail. So it takes a really long time to do the life or reliability analysis or lifetime modeling for capacitors. So as you can see, here you can see the capacitance change. Here you can see the ESR change. So blue line was the initial 0 cycle, but as it cycles more and more, you can see the ESR keeps rising. Another two just short projects I'll just explain. This is one what we call active cell balancing for lithium-ion batteries. So obviously the traditional cell balancing is using a resistive load. You just dump the power. With this kind of active cell balancing, what you can do, you can get the charge from the weakest, or which is highly charged. You can send that power back to the load, or you can charge the pack, the whole pack, just by circulating the power. And this kind of active cell balancing can have faster equalization, and also more energy can be stored in the battery. Final slide, this is the project we are doing. It's more aerospace, but can be implemented in automotive as well. So here, we trying to create optimized drive system for electric aircraft. So so essentially, future electric, like electric vehicle, the aircrafts will be electric. That's our view. And we try to find out from the aircraft model itself. So the student uses like a Cessna model, try to find out what's the optimum ratio of hybridization you need to reach certain distance or to get a certain range. So we do a lot of optimization of the whole system, then find out what's the battery voltage you need, what's the battery capacity you need. And based on that battery, so that's the electrical specification we get from the top level. And using that electrical specification, then we try to find out what's the inverter you will use, whether it's going to be 2-level, 3-level, what's the machine technology you'll use. The target is reducing the weight, as in aircraft, obviously the lesser the weight, the longer the range. Finally, I'd like to obviously like to say about my students who were doing all this amazing work. So as this group of students, I haven't gone through all the other projects because some of them are doing solid state transformer or resonant converter for electrically excited synchronous machines. So essentially the machines which doesn't need magnetic materials or rare earth materials because of the time constraint, but yeah, just wanted to recognize them. And also this group of students were working on the integrated packaging and the reliability projects. So just a summary, so wide bandgap devices can enable high power, high frequency, high power density, highly efficient power converters. And to achieve the greatest gain, our research says you need new topologies, new design techniques, and also new design tools. We've shown that integrated topologies, resonant converters could be solutions to meet the future power density targets. Obviously, we need to have a better understanding of these wide bandgap semiconductor devices to fully exploit their capability. We need to think about the EMC emissions and other performance issues. We've seen that integrated power module and proper health management could be one of the solutions. So thank you. Thanks for your time. Any question, please?
Thank you. Maybe on slide 26, we had info on the module reliability issue. So if you look at the heat sink there, it says the thermal grease and base plate contributes to a lot of thermal resistivity there, right?
The thermal grease. Yeah.
So can microchannel cooling be of contention here for microchannel cooling of the switches?
The heat sink can be any type. You can have microchannel cooling. You can have, we have seen techniques of adding pin fins directly to the DBC. For example, you can connect pin fins. Instead of base plate, you can connect pin fins there and try to cool it. But the problem will still be there. It's still, because you will have different materials, which will have different CTE. And when you have the delta T at the junction, all the different materials will, as I said, expand and contract at different rate, which will create reliability issues.
So can we not take an X-ray scan of it and see where the weak points are and then direct the solution to,
if you have wire bonds, if you have wire bonds, definitely the weak point is the hill.
So can we just speak only about that and then provide cooling there?
Well, that's not my research. So we have another researcher who is a material scientist who actually do the physics of this crack. So how the crack propagates, how crack initiates. Her name is Pearl Aguarca. Pearl. So if you see her papers, you'll see the physics of failure. So from my side, we are not looking at the physics of the failure. We are trying to more creating tool to do the health management and reliability assessment of this module.